The evolution of autonomous systems such as robots, drones, and self-driving cars has provided a renewed focus for sensor technology. Hello everyone, I'm James, the R&D lead at Calio, and today I'll give you a quick introduction to Calio and the cutting-edge 3D ultrasound sensor that we've developed. Then I'll walk you through how the technology works, and finally I'll show you how we're using AI to develop and generate LiDAR-like point clouds at the fraction of a cost. Calio has developed a novel 3D ultrasound sensor that delivers reliable imaging performance when other sensing technologies are impaired. Our sensor offers a low-cost, low-power solution that complements other sensing technologies which utilize lasers, radio waves, and optical instruments, adding an additional layer of vision for autonomous systems and vehicles. The evolution of autonomous systems such as robots, drones, and self-driving cars has provided a renewed focus for sensor technology for object detection, collision avoidance, and navigation. However, there's a big problem. All optical, laser, and radar systems have major performance limitations in challenging environments, such as rain, dust, and fog. This affects both the efficiency and effectiveness of current autonomous technology. Basically, vehicles can be rendered blind in poor conditions. Ultrasound, however, is less affected by varying ambient conditions and the reflectivity and transparency of objects. Our solution provides reliable 3D sensing where LiDAR and radar may fail, ideal for close-range perception and redundancy. The perfect complement to existing sensor stacks and multimodal fusion. This novel technology provides several applications within the autonomous vehicle space and plays an important role in shaping the future of the next generation of driver assistance and self-driving systems. We have demonstrated several applications and attracted interest from numerous industrial partners, including mobile robots, logistics, and warehouse sector. In addition, the technology has been extensively benchmarked against automotive-grade LiDAR and radar sensors, providing valuable insights into the different sensor performance. These experiments we conducted at UTAC in Millbrook, comparing the performance in rain and fog environments, revealed that both radar systems and LiDAR were rendered ineffective in harsh conditions, whereas the Calio Pulse sensor was still able to detect objects in the harsh conditions due to the longer wavelength of ultrasound being able to penetrate through the environmental occlusions. The sensor functions similar to how bats navigate in the dark, first emitting an ultrasonic pulse into the environment and then listening for the response and reflections. The data is then piped into the CalioSense SDK to generate 3D intensity maps and point clouds of the environment. For the automotive sector, we envision Calio Pulse replacing the typical 12 to 16 1D parking sensors, but delivering full 3D perception, providing the extra layer of environmental awareness and redundancy needed for the next generation of smart vehicles. In the video here, we have two pulse sensors mounted to a road vehicle driving through an urban environment, where you can see the rich Calio Pulse data being plotted on top of LiDAR, detecting surrounding vehicles, pedestrians, and objects along the side of the road. Already, the pulse data can be used to enhance perception for close-range safety, ADAS, and low-speed autonomy. However, there is still much more to be extracted from the ultrasound data. And this brings me to the core of this presentation, where I'll discuss how we can enhance the output from the pulse sensor. Here, you are looking at a 2D slice of the raw Calio Pulse data in a 2D environment, where you can see that often the data is not highly resolved and suffers from imaging artifacts resulting in banana-shaped objects and sparsity. Traditional filtering is typically used to remove these artifacts and clutter from the data. However, while it may appear as noise, often it contains additional information and context about the environment. So how do we minimize these effects without losing potentially useful information? Initially, we began to explore some analytical imaging algorithms which were able to enhance low-intensity reflections, however, still resulted in some artifacts and sparsity. Given the complexity of this challenge and the limitations of basic filtering, we started to look towards machine learning approaches for their ability to extract relevant information and from complex data patterns. This is where we developed Ultra HD, a custom convolutional neural network that takes in Calio Pulse data to generate LiDAR-like point clouds. On the screen now, you are seeing some preliminary testing in a simulated environment, where a vehicle moves through a warehouse simulating sensor data from both the Calio Pulse and a LiDAR. This data was then used to train the model using LiDAR as the ground truth, teaching the network to transform between the two modalities. After successful testing of Ultra HD in simulated environments, we continued the development of the model, but now with real-world data. This involved large-scale data collection, where we collected around 25,000 samples of LiDAR and Calio Pulse data, and retraining the model using this new data set. Here are some of the results from that process. Along the top row, you can see the raw ultrasound data used as the input of the model. The data was then transformed into LiDAR-like point clouds on the bottom row. It was able to produce point clouds with high structural similarity to LiDAR and completely remove sparsity and imaging artifacts seen in the raw ultrasonic data. The model was also able to generalize well, reducing the mean point cloud error by 80% in similar environments and by 60% in different environments. However, there were still some limitations. These experiments were all conducted in indoor environments and were only done in 2D. And there were also still some clutter in the data output. But with further filtering and dataset expansion, particularly in outdoor areas, we believe we can resolve these issues, allowing you to generate LiDAR-like point clouds at a fraction of the cost. We also conducted some additional validation of the model outputs, where we were able to demonstrate that you can not only enhance the pulse data, but you can also use industry-standard LiDAR algorithms on the model's outputs for tasks such as object detection, navigation, and mapping, aiding in the development of multimodal sensor systems. On the screen now is an experiment which used the model's predictions in a robotic mapping task, achieving high structural similarity to the LiDAR using standard LiDAR algorithms. However, that's not all you can do with the Calio Pulse sensor. Here is a simple AI classifier we trained purely on the Calio Pulse output. On the video on the left, you can see the detection of a vehicle, in the middle, the detection of a pedestrian, and on the right, a cyclist. We trained this perception system to detect and classify various types of objects in the environment with high accuracy, showing that the Calio Pulse sensor can not only detect if something is around you, but what is around you too. Similarly, we have been experimenting with an automotive use case, multi-occupant classification. Our model was able to distinguish empty seats, lone driver, 2 front passengers, and a mix of front and rear, and more. Even with open windows, heavy construction noise, and loud music playing in the vehicle, the sensor was able to capture reliably. And importantly, without the invasion of the occupant's privacy. And that brings me to the end of the presentation. Thank you everyone for listening. I hope I've been able to show you how much is possible with the Calio Pulse sensor, whether it's generating LiDAR-like point clouds or classification.